Welcome. Thanks for joining us this afternoon. I'm Liz McCullough from Pacific Science Center, and I'm your host for today's virtual Meet a Scientist event. Before we meet today's participants, I'd like to remind all of you that educational programming like this is made possible in part thanks to the generous support of donors. In the face of challenges like COVID-19 and climate change, science and an informed public are absolutely essential. To ensure that curiosity never closes, or for more information about donating to Pacific Science Center, visit PacSci.org/support. The scientists you'll be meeting today are members of our Science Communication Fellowship Program, which offers training and support for local STEM professionals connecting their work to public audiences. Typically, Science Communication Fellows deliver hands-on activities at our Meet a Scientist events twice a month at PacSci. While our doors are currently closed, we still wanted to give you the opportunity to meet some of the fantastic local scientists who have committed themselves to science communication. Today, our Science Communication Fellows will be discussing their experiences as professionals and as people. We have a few questions planned, but the conversation may go in all sorts of directions, and we want you to be a part of it. If you have a question or comment that you'd like to share with us and with other viewers, please put it in the YouTube live chat, and we'll make sure we address it. Now, please welcome to the live stream, Christine Kang, graduate student in the Department of Chemical Engineering at the University of Washington. Hi, Christine.
Hi, Liz.
We also have joining us today, Jarrod Canright, a graduate student in the Department of Physics at the University of Washington. Hi, Jarrod, welcome.
Thank you.
And finally, we have Taylor Stepien, a very recent graduate from the Department of Global Health at the University of Washington. Hi, Taylor.
Hi.
Congratulations and welcome.
Thank you.
All right, to get us started off, can each of you tell us just a little bit about what it is that you study and what work you do? Keep it brief because we have lots of other things to get to as well, but we'd like to just set a little bit of context here. So Taylor, you're our most recent addition to the live chat. Can you let us know what you study?
Yes, thanks so much. As you mentioned, I just graduated from the Department of Global Health, so I'm really excited about that. And I was in a program called pathobiology. So that means that we study pathogens that affect human health, infectious diseases. And even though that's really timely right now, unfortunately, I wasn't studying viruses, I was studying bacteria. I was looking at typhoid fever, but definitely really topical. And I'm excited to be part of the global health community in a crazy time like this.
Yes, very exciting time for that community, I'm sure. Jarrod, can you tell us a little bit about what you work on?
Sure. So I'm in the physics education group at the University of Washington, where we look at how students learn physics and how to best prepare teachers at the high school and at undergraduate and graduate level, how to best teach physics. And my angle on that is I look at the applications of virtual reality technologies in physics classrooms, looking at ways where we can, well, right now, looking at ways where we could kind of repair the damage from forced virtualization, where we kind of had to go online without any warning, but then also looking at how can we use virtual and augmented reality technologies to teach physics in ways that we can't otherwise.
Great. Christine, can you tell us a little bit about your work?
Sure. So I'm currently a graduate student at the Institute for Protein Design. And at the Institute, I use computers to design small building blocks made out of short proteins. And my ultimate goal is really to design these building blocks so well that I can mix them together in solution and they'll like automatically assemble into tiny 3D materials like a crystal or an empty cage.
That sounds really cool. For our next question, I'm going to actually kind of take the science out of it for a minute and just give people an opportunity to get to know a little bit more about you as people. So I want to know where you grew up. Let's start with you, Christine, this time.
Sure. So I grew up in the Portland area in Oregon. And yeah, that's pretty much where I grew up.
Nice. Jarrod, how about you?
I grew up in Fairbanks, Alaska, mostly. I spent 10 years there like splat in the middle of Alaska, and before that was kind of like hopping around the lower coast on and off the road system.
And I grew up in Wisconsin in a small to medium-sized town on Lake Michigan. And I also went to school in Wisconsin as well.
Great. So we have sort of a smattering of the western half of the US, including Alaska. Very nice. I am going to start off a little bit of our more science-focused questions by asking something that people kind of either love to hate or talk about usually, which is, what is the most memorable or entertaining way that you've messed up as a scientist? Does anybody have a good story that comes to mind?
Maybe I've just blocked it out of my memory.
Do you feel like you mess up as a scientist?
I think I can't think of like a huge mess up, but I think every single day there's always something that you think you could have done better, or something doesn't go the way that you planned and you have to figure out how to troubleshoot it. And I think that's the reality of a scientist that maybe not everybody realizes, is that more often than not things go wrong, and it's actually rare for things to go right. And it's a lot of just trying to figure out what's happening day to day. I don't know if Christine and Jarrod agree with that.
Oh, I totally agree with that. Like,
yeah.
When I hear this question, like, I want to give an example of like something like fun and interesting as a mess up, and like something that ended up being humorous. But I definitely screw up all the time. But generally, what that means is like, oh heck, I have to spend another 4 hours figuring out why this doesn't work. Like, it's not fun. Like, it's not exciting. Actually, one thing does come to mind to directly answer the question. So we were running some physics labs where we made up some physical phenomena such that they're simple enough that students could like be able to figure them out with the tools they had available, but they can't look them up. And so you can't actually know the answer when you start doing science, which is kind of what we're trying to prepare them for. But they were able to get like a bunch of these particles kind of spinning around and randomly. So they'd have these particles, they can create as many as they like, they can move them around, and they'd kind of like self-aggregate into these little structures that would spin around. And if you added enough, then that little structure would just explode, sending those particles everywhere. And we thought that that was due to like the wrong kind of particle getting in there. Like, students were coming up with all kinds of reasons. Turns out I messed up the physics code. There was a setting I did not properly configure, and so particles were getting inside of one another. And then the physics engine goes, oh, nope, can't have that, and applies a huge force to get them off. And then those two particles take everything else with them. So I suppose you could call that a feature of the physical system, but it certainly wasn't an intended one.
Yeah, in your case, it was messing up what you had intended to do.
It's not a bug, it's a feature.
It sounds exciting, though. Christine, what's your view on messing up in science?
I think I'm certainly, I think I'm with Taylor on this. Like, I definitely like mess up things every day. I mean, that's just kind of that seems to be a normal daily thing that happens as a scientist. And kind of what you always have to do is just find a way, either a hacky solution or an elegant solution. You have to find a way around it. It's really hard for me to think of like a mess up that I would consider to be funny, though.
That's fine. Jarrod's response to this got me thinking a little bit about, I'm curious about what your work looks like day to day. Are you mostly working on computers or in a virtual world? Like it sounds like Jarrod is some of the time. Are you mostly in a lab doing experiments at a bench? What does your day-to-day life as a scientist look like? Christine, do you want to start this one off?
Sure. Sure. So on a normal day-to-day basis, I'd say half my work is kind of in a lab, wearing a lab coat and goggles and all of the safety PPE. And then the other half is on a computer, kind of doing some coding or making these designs and things like that. But lately, because of the situation we're all in, I've been just working from home on my laptop. So it's been kind of fun. There's so many snacks to eat while I'm here.
Definitely a temptation of working from home for me too.
Absolutely.
Taylor, is that sort of what your work has looked like?
Yeah, I would say I would have expected me to spend more time in the lab than Christine or Jarrod, but I'm probably similar to Christine in that I spend most of the time in the lab, I guess, but some time on the computer as well. And since we are a microbiology lab, like you said, Christine, we have to wear all the proper protective equipment. So making sure the organisms that we're working with don't infect us, only the cells that we want them to. So yeah, lab coat. And I most often work in a biological safety cabinet, which is this huge box that has airflow in it such that the bacteria won't flow out of it and onto me. And that also keeps my cells inside of that box clean. So I spend a lot of my time working in that box, which is in a very small windowless room. So podcasts are my friend.
Nice. Does it take a lot of, compared to what you know about other kinds of science, working with infectious diseases, does that mean that you spend a lot more of your time on these safety protocols and things like that?
I think yeah, probably we do. I know we share a floor with some biochemistry labs, and I know they do a little bit of work with E. coli, but that's considered less infectious, I guess, than the stuff that we work on. So yeah, it's definitely an important part of it. Is
what
that
kinds of
safety
things?
Element.
What kinds of things specifically do you work with?
I work with the infectious agent of typhoid fever, which is caused by salmonella,
Okay.
which most people in the US don't know because it's not really a problem here.
But definitely infectious.
Yes.
Jarrod, I imagine a lot of your work is computer-based. Is that right?
Yeah, so in the before times, I spent the vast majority of my time in front of a computer anyway. Like collecting data, what collecting data looks like for me is putting a whole bunch of VR headsets in the classroom, like with a piece of software I've been working for a month to develop with like a piece of curriculum that myself and a team of people at the physics education group have been putting together. And then with a couple of TAs with whom we have had several conversations, like here's how you manage VR in classroom. Like there's a whole bunch that goes into like a 2-hour data taking period, and everything else is talking to people or at my computer.
Cool. We have a question that's been suggested here of, what do you wish other people knew about your field and about the work you do? Is there anything that like you're just dying to get out there into the world?
I have an answer kind of based on the current COVID situation, because as somebody who works in infectious disease, I had a lot of friends and family asking me questions, like, should I do this or should I do that? Is this safe or is this not safe? And I think the biggest thing I've noticed is the way scientists think about uncertainty is different than maybe the public does. And people really like to know definite answers, like, will I be 100% safe if I do this? And what I wish people would know about science is that nothing is ever 100% certain. And we try to express that, but yeah, I think all of science is trying to approximate things as best we can, but it's hard to ever know anything for sure 100%.
Is that something, Christine and Jarrod, that as scientists, you feel like you wish people understood better?
It's actually something that we try to be. So I work on making physics lab curriculum. That's something we're trying to incorporate in there more. Like, we try to never ever use the language like this experiment proves this. Now you have some understanding, some set of rules, some set of data, some set of relationships that tell you how something works. And you can design an experiment that tests an element of that model. And you can support that model or you can reject it. So it's really easy to, or not necessarily easy, but you can outright reject a model or a claim. But to prove a model or a claim just frankly doesn't happen. Like, there is always a chance that something has been missed. And no scientific claim can ever be 100% proven.
Right, and the scientific method is really about disproving, not about proving, which is something that in my experience, I find a lot of people don't really understand outside of the science world.
Mm-hmm.
Yeah, I think that I would agree with Jarrod a lot about that too. Like, even within kind of what I'm working on right now, a really big piece of what I've been thinking about lately is, let's say that I come up with a material and I'm able to see something, right? How do I prove that what grew or like what appeared, the material that I've come up with, is what I actually want and not just something else? And there are so many different experiments that are kind of available to use that you'd be able to use to give you a little bit more information, but not like 100% confident proof that everything is exactly the way you want it to be. Like, perhaps you'll do an experiment that'll tell you, oh, this is the approximate size of what you made. Oh, this is the approximate composition of what you made. But it doesn't necessarily mean, just because something has the right components or the same components, it doesn't mean that everything's put in the right way. So like, you can imagine a sandwich. You can say, I could do an experiment on something that I wanted to create a sandwich with, and look at it and say like, oh, well, the sandwich material that I've made has all of the right pieces. It has bread, it has, I don't know, like meat and cheese and mayonnaise and lettuce and tomatoes and things. But if it's not put together in the correct way, it's not quite a sandwich, and it's not quite what I want. So it's kind of interesting. Like, a lot of what we do as scientists, at least in my field, is looking at ways you can use different techniques to like get more evidence about whether what you got is what you want or not.
A couple of you alluded to the current situation with COVID-19 in some of what you've shared with us already. So Jarrod, you're not able to access the classes that you normally would, and Christine, you're doing more work from home. Are there other ways in which you feel like COVID-19 is impacting your work or just your life in general? I know, Taylor, you were defending your dissertation as all of this was going down. How did that work out?
Yeah, I would say that was definitely a huge effect that it had for me. So for those that don't know, usually when you are earning your PhD, you have to present your work in a talk that is open to the public, and many students kind of look forward to this as a celebration of their work in person, and their friends and family sometimes attend. And so for me, that was all done by Zoom. But it actually turned out to be kind of a blessing, because there were people who watched it who maybe wouldn't have been able to come to the real thing. And yeah, it actually felt kind of like people came together, and even though we couldn't see each other in real life. So yeah.
So it was a different experience, but still a good experience.
Yeah.
Nice. Christine and Jarrod, any other ways that you haven't shared yet in which you feel like you're focusing on different things these days, or just having to do your work a little bit differently?
Sure, I
So
can go first. Oh, okay, or you can go first, Jared.
this is, I was about to talk about, thank you, this is the perfect evidence for the point I was about to make. Group work over Zoom is really hard because you're constantly repairing the interactions you have with other people. It's hard to kind of foster like a shared sense of belonging and like as a community of practice, as a group. And so I'm trying to figure out how we can use like embodied virtual reality, like with like avatars in virtual space as an alternative to group collaboration over Zoom. Both as a way both to respond to what I would call forced virtualization of curriculum, where all UW classes are online now, but they certainly weren't designed to be that way. And also for intentional design of new educational tactics that might be enabled by this technology. So that's something I've been interested in for a while, and now I am actively working on that because it is timely.
Cool.
Sorry, Christine, you go ahead.
No, thanks. That's actually awesome. I hope you are really successful in that project, because I would love to like be able to use VR to like hang out with my with my work coworkers and my friends at the lab during this time. I noticed that that's something that I really miss. Like I miss the interaction that I get to have with all of my work colleagues. Since we're all kind of working from home, and so now whenever we want to have an interaction with each other, we want to talk to each other about something, it has to be way more deliberate. Like we need to like schedule a Zoom call, somebody has to send a link. There's all of this additional work that's required in order for me to like go hang out with my friend and ask him about his project and how he's doing. It's really interesting and kind of hard. So a VR way of setting that up would be so cool.
Yeah, I agree, Christine. It feels we still have meetings and talks you can watch, but it's really different than just being in that community of other scientists and, you know, passing someone in the lab and being like, hey, did you see that recent paper? Or talking to your boss about a cool finding you have. It's just, yeah, it's an adjustment to the way that you interact with your colleagues, and it's challenging.
I never realized just how valuable the passing in the hall conversations were to not just socialization, but like keeping current with the group, and like as a resource when I have questions about things I'm doing or vice versa. Like the absence of that is really hard.
Yeah.
We're getting some audience questions. Thanks, viewers, for submitting questions. Keep them coming. Let's tackle, what big question is your work seeking to answer? Anybody want to take that on first?
I'll go. Okay, so I study the way that typhoid fever interacts with the human immune system. And this is, I think most infectious disease studies look at this particular phenomenon. So how does the bug that causes disease interact with the human immune system? And it's because we can't really begin to develop new therapies or vaccines if we don't understand this fundamental interaction. So like, for example, right now, there's so much effort into developing a new vaccine for COVID-19. And we know some of the basic immune responses that are associated with a successful vaccine. But I think long-term, there's going to be a lot more people really studying these kind of viruses to sort of fine-tune those sort of therapeutics. So my work is focused on one particular bug, but a lot of what we learn about only one bug can apply to multiple different pathogens.
Definitely a big question.
Mm-hmm.
Jarrod, how about you? What big questions are you taking on?
How do we effectively use new virtual and augmented reality technologies in physics educational contexts? So to expand on that a little bit, I feel like there's a lot of ways to use them ineffectively. Generally, if as a rule of thumb, if if a proposed piece of curriculum that uses virtual reality technologies, only justification for that is it's this, but in VR, then there's not really a basis for the additional effort and overhead that goes into bringing that technology into classrooms. And thus it should be perhaps the effort that went into all of that perhaps should be reconsidered. However, there's a lot of interesting ways I've been looking at where it can be uniquely useful. That is, it is the only medium in which a certain tactic can be used in education, and perhaps those tactics, because we haven't been able to do them before, can be distinctly useful. As I was mentioning earlier, one of the primary ways we're looking at that is just making up physical phenomena that aren't Googleable. And only a handful of people actually know the answers. And so we can make them fairly simple, such that students with minimal physics background can still have the tool set to begin to approach them and begin to develop models, both qualitative and quantitative, about how they work. But they can't possibly know the solution. And so we can focus much more on that process of developing models, on constructing a scientific experiment from which that will give you evidence to support or reject a piece of a model. And rather than a kind of cookbook lab where you are kind of finagling equipment to try and get to a number that other scientists have spent a lot more time and effort coming up with prior to that.
Can you give us an example of the kind of phenomena that you're trying to get across in these virtual experiences?
Yeah, so one phenomenon I generally start from when designing these experiences is electric attraction repulsion. So if you have a object that is, so objects can have a positive or a negative electric charge, and two positively charged objects will repel, two negatively charged objects will repel, a positive and a negatively charged particle will attract. And so we decided to come up with something adjacent to that. So where we can say, oh, this object has this quality, and it interacts at a distance with other objects that have that quality, which is governed by some function. And that function in context of electricity is Coulomb's law. So if you double the distance between, so the amount of charge on both objects affects the amount of force they experience, or how hard they push or pull. And then if you are to double the distance between them, that force gets divided by 4 in its magnitude. It becomes only a fourth as strong. So we say that that goes as 1 over distance squared. So double the distance, you divide the force by a factor of 4. And so we came up with a new particle we called the Minty particle, which produces a Minty field through which Minty particles interact with each other. And we decided to give it some distance at which there isn't actually any force between them. And if two Minty particles come closer to each other, then they will repel. But once they get back to that that threshold, if their distance gets beyond that, then they begin to attract again. And so you end up with kind of little oscillating behavior around some certain distance.
Cool.
And it's governed by a fairly simple function, which we had students doing quantitative analysis to try and figure out what that function was.
Nice. It's nice to be able to kind of picture what you're having students work on in this virtual reality.
Mm-hmm. They're just like little green spheres floating around, but they had a lot of fun with it.
Nice. Christine, what big questions are you trying to answer in your work?
Ooh, okay, so kind of how I guess Jarrod, just to relate to some of the things that were talked about. So kind of in the way that Jarrod is trying to teach students about different phenomena. Part of the work that folks in my lab are working on is trying to come up with appropriate models that we can use, so that instead of just trying to understand the phenomena, we can then use what we know about all of the interactions between each of these different phenomena to be able to make things from scratch. Because the best way to make sure you really understand something and you understand how it works, is to kind of build it from the ground yourself. And if you're able to build it in a way that results in the same kind of thing as what you kind of inspired that structure, then that means you really understand how the object itself works. So we have, there are a lot of smart people who've come before me in our lab that have put a lot of work into developing a series of different algorithms and models to be able to predict if you have a group of molecules interacting with each other in a very specific way, or proteins interacting with each other in a very specific way, what those proteins will look like. And what I'm doing now is I'm trying to make new proteins and new peptides from scratch. And so really what I'm trying to kind of, I guess the big questions that I'm really interested in is, how good is our model for being able to like make new things using the same principles that we already know some information about? And then also, what new things can we learn, and new criteria and new rules can we learn about what's really important or what features are really important for us to be able to make what we want from scratch in the way that we want it to.
So kind of testing what we think we know about the world in order for us to make progress beyond what we currently have.
Exactly. And to be able to like use what we know to be able to make new things that we've never seen before.
Great, that sounds awesome. Taylor, we have a specific question for you from a viewer who is named Ray and is 6 years old. Are there any germs that you study?
I do study germs. The organism that I study that causes typhoid fever would be definitely considered a germ. But something that's really exciting in my field that some other scientists who study germs are interested in is what makes something a germ, which we think of as something bad, versus just a small thing that's actually good for us. So some of the things that we consider gross and germs are actually part of our bodies all the time. For example, in your gut, you have millions and millions of germs that are actually helping you digest your food. And so it's a really interesting thing for scientists to try to understand the difference between the things that might help us do stuff like digest our food versus things that might make us sick. So thanks for that question.
So some germs are bad, but not all germs.
Yeah, and some germs can be bad sometimes, but good other times. It can be confusing. Why we're studying it.
Okay. We were talking a little bit earlier about how we kind of all miss our colleagues and seeing them in the hallway, partly for scientific work, but partly just to connect with them and see people and be around people who care about the same things we do. What are other things about your work that are rewarding or that you enjoy doing?
I actually really like teaching and outreach. It's part of why I was so excited to be part of this fellows program, but I think obviously all of us are really excited about what we do, but if I can tell it to somebody else and get them equally as excited, that I just love that part of it.
Jarrod, how about you? What do you find rewarding about the work you do?
It kind of lets me tie my interests in physics and in science into my interests in gaming and VR. So those interests kind of co-developed, but without intersecting so much for a long time. And now finally with this project, I'm really able to bring all the time I spend thinking about both of them into the project. And so it's a project very well aligned with what I like to do for fun and also what I'm interested in as a scientist. And I am so grateful to be able to be in that position where both of those kind of aspects of my identity are engaged in the work I do.
Yeah, it's great that you're able to find a way to kind of combine everything together.
Like physics-based games like Portal or like Slower Speed of Light are just my absolute favorite, and I would love to actually go into making those. And so as a potential kind of path for me in the future, this project has helped me develop an understanding of how do people develop their concepts of physical ideas based on observation. And I'm really excited to see where that goes.
Christine, what do you find rewarding?
I think that I can probably categorize them into different ways. So, like Taylor mentioned, I think that being able to do outreach and like talk to other younger scientists about just science in general and seeing them be so excited about it, I think that's really it's really great for me, because sometimes, often as scientists, as we talked about, like we make mistakes all the time. Sometimes things just fail, and sometimes many things fail in a short period of time, so you get a little bit down. But when you are able to share your science with other people and see how excited they are about the potential for your work or something like that, or just kids who are really excited about making lavas and things like that, I think that that's something that really invigorates me and gets me really excited. The other thing I think is kind of rewarding about my lab in particular is that we all really like snacks, and I miss that a lot. Like we used to have, after we would have group meeting presentations, we would have like junk food and like cheese and crackers and stuff like that after the meeting, so that we can all kind of come together and talk about the presentations we've heard, or just chat with each other about TV and other things that we like doing outside the lab. And I definitely miss both the community of those experiences and also the snacks.
Did you have better snacks at work than you do at home?
I think I have more variety of snacks at work, and I think that the variety is something that's very exciting. It's its own reward.
Nice. We have another question from the viewers, which Christine, you actually kind of started to answer a little bit. Amazing segue here. What advice do you have for any potential future scientists who might be watching? You can start if you'd like.
Sure, I'll start. I think that the advice that I have for future scientists is that it's not bad to fail. Failure is normal. It's about what you do afterwards. Do you pick yourself up and keep going, or do you just give up? Failure is just an important key part of continuing on in science, because science is hard, and that's why so many people like to work together on these really hard topics.
Great.
Yeah,
Taylor,
I definitely agree with that. I don't think anything can really prepare you for the amount of daily, not failure, but just things happening that you don't expect. So I think there's a distinction between being really interested in a subject and being somebody who's really interested in problem solving through that subject. So I think the interest in something like biology will get you there, but the interest in really truly understanding every small detail of something is what's going to take you all the way. So just be willing to ride that ride and know that it's going to be unexpected.
Jarrod, do you have any advice for young potential scientists?
Definitely agree with Christine and Taylor's advice. Both of those are definitely so good to keep in mind. One thing I don't hear a lot I'd like to mention is that science happens by communities. Nobody goes at science alone. Construction of knowledge is a social thing. Science happens in communities of practice where people are always supporting each other, even if not directly collaborating, having people to bounce ideas off of, having other people around with enthusiasm for the things that you work on to keep you energized. All of the all of those things are are really essential elements to scientific practice. And so you see in a lot of media the idea that science is one really, really smart person going it alone with a giant fancy. That doesn't happen. This doesn't exist. Knowledge is formed by people, not persons, by people. And that's present at every level of the scientific process, from formulating ideas to start testing, to asking for resources to start those tests, to interpreting the results of them and running them by other people in the field to get them published in a journal and acknowledged as part of that field. Sorry,
Yeah.
Chloe.
No, that really resonated strongly with me. I think you're spot on that it really takes the whole community. And a huge piece of advice I would give to someone who wants to be a scientist is be willing to ask for help and know when you need to, and don't feel like, it's all about you just working as hard as you can and being as smart as you can, because you're right, like the most successful scientists are the ones who know when they need to ask for help, know the people that they can ask to collaborate with them, and also like sharing those successes with your collaborators and really like building up other scientists instead of working against them.
Great, yeah. We're so happy that you're part of the scientific community. We're happy also that you're part of our PacSci community. And for the last question that we're going to address today, I am going to ask you what your favorite PacSci memory is. I'll let whoever has a good one ready get started.
I can go. I don't think that I have just one favorite PacSci memory. I've always really enjoyed doing Be the Scientist at the Pacific Science Center because it's kind of one of my main opportunities to be able to talk to students and young people and younger scientists and kind of hear what parts of my work or what parts of even just the Pacific Science Center itself that they're really excited about. I really like when kind of our tables are situated in the room that's next to the butterfly gate, because the butterfly room, because I get to see people coming out and being really excited about butterflies, and I think that's a lot of fun. Yeah, I really miss it. I really do.
Yeah,
We miss
me
you
too.
I really miss the what is reality space. I think my favorite memory of PacSci, like not a specific instance, but more an extended experience, was being a volunteer almost every week in the what is reality space during its formative days. So I started my involvement with PacSci as a volunteer rather than a science communication fellow. And started in science interpretation, like rotating around the tide pool and places like that. But then since I was just starting to explore VR and physics education, I was really interested in getting in and helping with the what is reality space as the Pacific Science Center staff kind of explored what that space was going to become. And as part of that, I spent a lot of hours running the HTC Vive VR cart, where we just had like a bunch of different experiences that we could pull up for people, basically just like a little VR arcade. And I got to see so many people try VR for the first time. I got to see like 4-year-olds who we just gave like a single Vive one, like painting a tilt brush and having just a fantastic time. I got to see older folks who had moved away from their country like at a young age and never been back, be able to go in Google Maps, like the 360 mode, and like go see the house where they grew up. And so many other people's experience is like, one thing I forgot to mention earlier about the rewarding parts of my work is seeing people use VR for the first time. There's this there's this characteristic excitement they all get, every single person, regardless of background, the first time they try VR. It's so cool to see, and I really miss getting to be a part of bringing that experience to people and the what is reality space at PacSci.
My first time in VR was also at PacSci. It was amazing. Taylor, what's your
Yeah.
favorite memory?
I would say I have a particular family that I remember came up to my Meet a Scientist booth, but their experience kind of embodies what I enjoy most about it, is those people who just kind of, they wander up and they're not maybe like looking specifically for what you're talking about. They kind of just wander by and are like, oh, what is this? But through talking to them, they get more and more engaged, and you end up having like this great conversation. And I think knowing that that was kind of unexpected for them, but then it ended up being something really positive, is like really rewarding for me. And it just shows how I think being open to learning about anything, even if it's not something that you thought you were interested in, can be like really interesting and exciting.
I feel like that's a great note for us to end on. And obviously, virtual programming is new for us at Meet a Scientist. So thank all of you for being willing to participate in this today. Thank all of you viewers for joining us today and sharing your great questions. We would love to hear your feedback about this program. So if you have a moment and could fill out the survey linked in the YouTube description, we would love that. Also, for more online content from PacSci, you can tune in tomorrow for our experiment with a virtual curiosity expo. That will be happening from 10 a.m. to 3 p.m. The focus is engineering, and you can find more details at pacsci.org. That's all we have for you this week. Thank you again, and see you next week. Bye.